Welcome to Theory of Computation. This is lecture number 40. In our last lecture, we looked at quantified Boolean formulas. And then we defined a language, TQBF, which consisted of the encodings of all quantified Boolean formulas which are true. In other words, we defined a computational question. The question was, given a quantified Boolean formula, we want to tell whether the formula is true or false. Now this question turned out to be p-space complete. Well, let's think about what that means. This means that if somebody were to design a polynomial time algorithm for quantified Boolean formulas or for determining if a quantified Boolean formula is true or not, then they would not just have a polynomial time algorithm for this one particular problem, but they would show that the whole class P space is equal to P. That means any problem that can be solved in polynomial space will also be solvable in polynomial time. This is a far-reaching consequence. And just like the theory of NP-completeness gives us evidence that NP-complete problems are not in P, that it is not possible for anyone to design a polynomial time algorithm, it gives us evidence, not proof. Similarly, the theory of p-space completeness gives us evidence that quantified Boolean formulas cannot be distinguished between the true ones and the false one. We cannot distinguish between quantified Boolean formulas in polynomial time. In fact, when somebody proves that a problem is p-space complete, they're giving even more evidence than if they were to just simply prove that the problem is NP-hard. Because all p-space complete problems are also NP-hard problems. Thus, if a problem in p-space happens to admit a polynomial time algorithm, that has even more consequences than if a NP-complete problem happened to admit polynomial time algorithm. Therefore, these problems are extremely general. Now, one of the central theorems in the theory of NP-completeness was the Cook-Levin theorem. The Cook-Levin theorem showed us that SAT is NP-complete. The theorem that we proved that QBF is NP-complete has the same standing as far as space complexity is concerned as the Cook-Levin theorem had for the theory of NP-completeness. The Cook-Levin theorem identified one problem, namely satisfiability, which is NP-complete. This, what it did was, it moved us from a whole complexity class to one particular problem. And as you know, the name NP-complete suggests that satisfiability is a problem in NP, and it's complete in the sense, in the weak sense that it has enough complexity to capture the whole class NP. And of course, similarly, we have the theory of p-space completeness, and we have moved from a whole complexity class to one particular problem, namely QBF. QBF has enough complexity to somehow capture the whole class p-space. We also noticed something else about quantified Boolean formulas. We realized that satisfiability is a special case of quantified Boolean formula. If we consider quantified Boolean formulas and we restrict ourselves to only existential quantifiers, then we get satisfiability questions. So if you have a formula which is there exists x1, x2, x3 all the way up to xn such that phi of x1, x2 up to xn is true, that is, you can view it as a quantified Boolean formula in which all the quantifiers are existential, or you can view it as a satisfiability question where it is being asked, is there an assignment of the variables which makes this formula true? In that sense, quantified Boolean formula, this problem is a generalization of satisfiability. Of course, we were easily able to see that satisfiability is in NP by simply saying we can guess the assignment. We can simply guess the assignment of the variables and check whether it makes the formula true. because checking, given an assignment, checking if a formula is true can be done in polynomial time. However, for quantified Boolean formulas, if you try to find an algorithm, a non-deterministic polynomial time algorithm, well, probably you're not going to succeed, because it's widely conjectured that the class P space is much larger than the class NP. On the other hand, what you can do is you can write down very simple recursive algorithm which will tell you whether a quantified Boolean formula is true or not. If you compute the time complexity of this recursive algorithm that we studied, if you compute the time complexity, you would realize that it takes exponential time. However, if you compute the space complexity of this algorithm, you realize that it takes polynomial space. And therefore, you would be able to show by writing down this trivial algorithm, this trivial recursive algorithm, that QBF is in P space. The hard part of proving that QBF is P space complete is actually showing that every language in P space can be reduced to QBF. Of course, this theorem, which says that every language in P space can be reduced to QBF, is a deep theorem. In this case, it has the same level of difficulty as the Cook-Levin theorem. Well, the Cook-Levin theorem is more celebrated than this particular theorem of P-space completeness because it has to do with ideas. Cook-Levin theorem historically came before the P-space completeness of QBF was proved. In fact, when the Cook-Levin theorem was proved, it was shocking. It was the first time people had looked at complete problems. It was the first time people realized that one particular problem can actually capture a whole complexity class. And of course, the proof of P-space completeness of QBF also uses ideas from Cook-Levin theorem. If you roughly look at the structure of the proof, the Cook-Levin theorem essentially makes a formula which is satisfiable if and only if from the initial configuration of the Turing machine you can reach a final configuration. But it does that by saying that there is a computational history, or what Sipser calls a tableau, an accepting tableau for the non-deterministic Turing machine. And this can be expressed by a satisfiability question. What we did was we started doing a similar thing to prove that QBF is P-space complete. However, in this case, the Turing machines that we are dealing with are not non-deterministic polynomial time Turing machines, but they are even more complicated than that, even more complex than that. The only thing we know about these Turing machines is they require polynomial space. We have no guarantees on how much time do they require. Thus, if you write down a computational history on a given input for such a Turing machine, it would be exponentially, it can be exponentially long. Each configuration will have polynomial length, but the number of configurations would be exponential. Then we used two ideas to express whether such an accepting computational history exists or not using QBF. The first idea was just to do what we did in the Cook-Levin theorem. And the second idea was, since this computational history was exponentially long, we did some sort of a binary search. We said that if we can express the fact that we can reach from a given configuration to another configuration in k steps, then we can use recursion. If we can reach from configuration C1 to C2 in k steps, if and only if there exists another configuration C prime, such that if we can go from C1 to C prime in k over 2 steps and C prime to C2 in k over 2 steps. And then we realized that in quantified Boolean formulas, we were allowed to use an existential quantifier. And that's a critical place where the existential quantifier was useful. However, when we build the recursion, we realize that the final quantified Boolean formula that we would get will have length that is going to be proportional to the number of configurations in the computational history, which was exponentially long. Thus, this kind of binary searching, in some sense, reduced the depth of the tree, but not the total number of nodes. The total number of nodes still remained exponential. And that's where we pull out a trick. We use the universal quantifier very, very cleverly in order to not duplicate the two sides of the tree. What we do is, instead of saying that we can reach from C1 to C prime in k over 2 steps, and from C prime to C2 in k over 2 steps, we say that we want to reach from C to D in k over 2 steps, where C and D come from a set. And this set is, of course, C1, C prime, and the second pair in the set is C prime, C2. So now the formula is not repeated twice. And what we do is we say, for all pairs in this set, we should be able to go from C to D in k over 2 steps. This removes the duplication in the quantified Boolean formulas, but we can remove this duplication only if you're allowed to use the universal quantifier. And what this does is this reduces the size of the quantified Boolean formula to a polynomial, and then this becomes a polynomial time reducibility. Of course, what was critical here was the use of the existential and the universal quantifier. The same proof technique that we have used here will not work if you want to prove that SAT is p-space complete. Why would it not work? Well, the reason is, in satisfiability, you don't have a universal quantifier, and you would not be able to get the length of the formula to come out to be polynomial. Therefore, this formula, this problem QBF, is a very central problem, and this theorem is very important. It has shown us how to reduce any language in p-space to QBF. Now, suppose what we want to do is we have another candidate problem, and we suspect that this problem is p-space complete. We don't have to reduce every problem which is in p-space to our new problem. What we can do is we can simply reduce QBF to our new problem, and that would show us that our new problem is p-space hard. Then, of course, if we can come up with a polynomial space algorithm for our new problem, that would establish that this new problem is also p-space complete. In order to prove that a new problem is p-space complete, all we have to do is reduce QBF to it. Once we show a polynomial time reduction from QBF to a new problem, then we establish that our new problem is p-space hard. And then if we can come up with a polynomial time algorithm for this new problem, then we establish that the problem is p-space complete. Of course, this recipe works because polynomial time reducibility is transitive. If A is polynomial time reducible to B and B is polynomial time reducible to C, then A is also polynomial time reducible to C. What we can do is now use these ideas, start with QBF, and start building a whole collection of p-space complete problems. As we view more and more p-space complete problems, that would give us some idea about what is it essentially that makes a problem p-space complete. By looking at a lot of concrete examples of p-space complete problems, we'll be able to sniff out some kind of a similarity. If we think of the theory of NP completeness, you would realize that there was something oddly similar about many of the NP complete problems. Satisfiability was saying, does there exist a satisfying assignment? Independent set was saying, does there exist a set of vertices which is independent? Does there exist a set of vertices of a given size? 3 colorability was saying, does there exist a assignment of vertices to 3 different colors which satisfies some property? Hamiltonicity was saying, does there exist a Hamiltonian cycle in the graph? So in some sense, the existence of some kind of a substructure in your problem sort of makes the problem fall in the class NP. Now, if the problem happens to be general enough, then it turns out that it becomes NP complete. Right now, we do not have many problems that we know are P-space complete. In fact, we have only one example. But if you think about this example is saying a bit more than just, does there exist? It is saying, does there exist for all? Does there exist for all? Does there exist for all? So in some sense, there's alternating choice between quantifiers that is happening, and then it's asking some kind of a polynomial question. So problems that are P-space complete follow this particular trend. So what we will do today is look at formally what QBF is. We'll review its definition, and from then on we would start looking at 2 other problems which are P-space complete. One of the problems is called formula game, which is very, very closely related to QBF. In fact, it is actually just a reformulation of QBF in terms of games. And the second problem that we would look at is called generalized geography, which is a game, which is an abstraction, a mathematically precise abstraction of a game that turns out that the computational question behind it is P-space complete. So let's begin our lecture. A formula phi equals for all x there exists y, x or y, and x bar or y bar. These kind of formulas were called fully quantified Boolean formulas, and they are either true or false. Once we have defined fully quantified Boolean formulas, then we can easily define TQBF. TQBF is the collection of all quantified Boolean formulas which are true. Thus, the computational question is whether a given quantified Boolean formula is true or not. Last time we proved the following theorem. We proved that TQBF is P-space complete. And now what we want to do is ask if there are other P-space complete problems. So we have one P-space complete problem, and now what we're doing is looking for other P-space complete problems. The answer is, of course, yes. So let's look at a problem that is very, very closely related to TQBF. Suppose we are given a quantified Boolean formula, and this quantified Boolean formula has the following form. It's of the form, there exists x1 for all x2, there exists x3 for all x4, and so on, all the way up to there exists xn, and then there's a psi, which is a quantifier free part of the formula. Once we are given this quantified Boolean formula, we can think of a game called formula game. So now we have taken a quantified Boolean formula in which variables appear with alternating quantifiers, and then there is a quantifier free part. And once you give me this formula, what I'm going to do is define a game between 2 players. And this game is roughly defined as follows. There are 2 players in this game, player 1 and player 2, and the game proceeds as follows. Player 1 assigns a value to the first variable x1, and after that player 2 assigns a value to the second variable x2. Then player 1 assigns a value to the third variable x3, and then player 2 assigns a value to the fourth variable x4, and the game continues like that. So if the quantifiers alternate, then the first player assigns the first variable, and after that, once he has chosen his assignment, made his assignment, then the second player assigns a value to x2. And after that, once that assignment has been made to the second variable, the first player goes back and assigns a value to the third variable, and the game continues like that. Player 1 assigns the odd indexed variables, and player 2 assigns the even indexed variables. But it is not true that player 1 assigns all odd variables in one go. He just assigns the first variable and waits for the other player to make his move. The other player assigns x2 and then he assigns x3. In general, we can define the game, and now we're looking at the case where a quantified Boolean formula is given to you and the quantifiers do not alternate. Then we define a slightly different game, and this game is going to be as follows. xi is going to be assigned by player 1 if it turns out that xi is existentially quantified, and xi is going to be assigned by player 2 if it turns out that it is universally quantified. Thus, if there are total n variables, then there are going to be n rounds, and in every round we look at the ith quantifier. If the ith quantifier is an existential quantifier, then it's player 1's turn. If the ith quantifier is a universal quantifier, then it's player 2's turn. And whenever a player gets a turn, he gets to assign a value to the variable xi, and these are Boolean variables, so the only possible assignments are 0 or 1. Once the n rounds of this game finish, all the variables have been assigned values. Therefore, we can look at the quantifier free part, psi, under this assignment. And psi is going to be either true under this assignment or false. Now, if psi turns out to be true, then we will say that player 1 has won the game. And if psi turns out to be false, then we would say that player 2 has won the game. This kind of a game is called a two-player perfect information game. An interesting question to ask is, who will win this game? We have to pose this question carefully. So suppose what you can do is you can write down a quantified Boolean formula and you can play this game with one of your friends, and what you can do is you can become player 1 who chooses the existential variables, and then your friend can become player 2 who chooses the universal variables. You can have a formula in which existential and universal quantifiers alternate, so you would take alternate turns assigning variables. At the end of n rounds, if there were n variables, you would look at the formula. If it was true, then you would win. If the formula is false, then your friend would win. Now, as you play this game, you can play this game on one formula several times. You can play it once, and then the next day you can play it, and you can play it in different ways. Now, sometimes you would win, and sometimes your friend would win. However, the question that we want to ask is, what would happen if you were to play perfectly? So if you had infinite power, infinite intelligence, then how would you play the game? And what if your adversary, player 2, also played with infinite intelligence? In that case, it turns out that the outcome of the game is not dependent on how you would play the game, but it is something inherent inside the game. So for example, let me remind you of a very simple game, a two-player perfect information game that you play, which is called tic-tac-toe. Tic-tac-toe is a game which is played on a 9x9 squares, and player 1 and player 2 take turns, and you put either a cross or a circle. And both the players are trying to get a 3 in a row. If you get 3 crosses in a row, you win. And if your opponent gets 3 circles in a row, then the opponent wins. This is a perfect information game. However, in this game, there are 3 outcomes. One is that player 1 can win the game. The second is player 2 can win the game. And the third is that the game itself can be a draw. Now, if you have played tic-tac-toe, a 3x3 tic-tac-toe, which is the household version, you would realize that the game is not very interesting at all. If 2 good players are playing it with sufficient care, then the game always turns out to end in a draw. Thus, if intelligent people, if you play with perfectly, then the outcome of the game is determined by the game, not how players would play. In the game QBF, there are only two possible outcomes. There is no draws allowed, because at the end, the formula would either be true or false. If it's true, the first player will win the game. Otherwise, the second player would win the game. So let's look at a simple example and see what's going on. Let's get back to QBF. So here we have a formula psi of x1, x2, x3. So in this game, let's say there are three moves. Player 1 chooses x1, and then player 2 chooses x2, and then player 1 chooses x3 again. At the end of the game, we'd have assignment of these three variables. If psi becomes true, player 1 wins. Otherwise, player 2 wins. So in this game, player 1 has a goal. He's trying to make the formula psi true. Player 2 has a goal. He's trying to make the formula psi false. At the end of the game, only one of the outcomes is possible, that is, psi under that assignment would either be true or false. So there will be no draws in this game. Now player 1 wants to make the formula true, and on the other hand, player 2 is trying to make it false. If player 1 wants to win, then he should find x1 such that for any choice that is made by player 2 for x2, he can find x3 such that psi is true. So in this tiny game, player 1 is trying to find x1 such that no matter what move player 2 makes, no matter what choice of x2 player 2 makes, he can then find an x3 which makes this formula true. If he can find such a x1, then that would be his first move. And then the player 2 will, no matter what choice he makes, he'll be able to then win the game from there. So this game, in which we have a quantifier-free formula psi, in some sense is equivalent to a quantified formula phi, where we add quantifiers to this psi. Thus, in this case, determining if player 1 wins is equivalent to determining if the quantified Boolean formula, there exists x1, for all x2 there exists x3, psi is true or not. If this quantified Boolean formula is true, then there exists an x1, so there exists a move for the first player such that for all x2, so for all moves of the second player, there exists a move for the first player which makes formula true, which means that he wins the game. In general, now if there are many variables and we have a QBF, so now we have a quantified Boolean formula. We have a first quantifier with the first variable q1 and second quantifier q2 with the second variable all the way up to the nth quantifier with the nth variable, and then we have a quantifier free formula psi. Now this is going to be an n round game in which two players will play n rounds. In the ith round, if the quantifier happens to be existential, then player 1 chooses the value of xy, otherwise player 2 chooses the value of xi. Then player 1 has a winning strategy if and only if the QBF in question is true. This is very clear because if the formula phi is true, then the player 1 can choose a winning move. And if the formula phi is false, then no matter what first move the player 1 chooses, there is a way for player 2 to beat him. So, in other words, what we are seeing is that every quantified Boolean formula defines a game, and we would call this a formula game. So, if I give you a quantified Boolean formula, there's an underlying game that I'm also giving you. The underlying game is there are n rounds in the game, and in the ith round, if the ith quantifier is existential, player 1 will make a move. If it's universal, player 2 will make a move. And the goal of the games are defined as player 1 wants to make the formula true and player 2 wants to, in the end, make the formula false. So every quantified Boolean formula defines a game, a formula game, and every formula game this way is given by a quantified Boolean formula. Now what we can do is we can define simply a language. This language is formula game, which is the collection of all games which are won by player 1. Therefore, now the computational question that we are asking is, given a formula game, determine if player 1 will win it or player 2 will win it. Of course, here once again we're talking about perfect play, that both players play perfectly. Then the question is, given a formula game, who will win it? Now the discussion that we have done so far tells us that player 1 will win the formula game if and only if phi happens to be true as a quantified Boolean formula. Therefore, the question of who wins the formula game is exactly a reformulation of the question of whether a quantified Boolean formula phi is true or not. So the observation that player 1 wins if and only if phi is true gives us our new theorem, which says that formula game is also p-space complete. In fact, formula game is nothing but a reformulation of TQBF, and therefore it is p-space complete. Now why did I spend so much time if this problem just simply happens to be a reformulation of QBF, quantified Boolean formula, or TQBF, to introduce this new terminology of games? Well, because let's think about what kind of a game formula game is. It's a game which we will call a perfect information two-player game with no draws. And what we do is we assume both players play perfectly and we want to figure out who will win the game. And this particular game turned out to be p-space complete. So this leads to a very natural question, that here is a game that we find is p-space complete. What about other games that we play? What about other games that are played between two players? Do they have any such complexity theoretic characterization? Are some of the more familiar games p-space complete? So this is a very interesting question, and we'd look at one other example of a game which is natural, and when you formulate the game precisely in terms of graphs and mathematics, that version of the game turns out to be p-space complete. So in general, there are many two-player perfect information games. Most board games are like that. For example, chess, checkers, Go, etc. are perfect information games. But card games are usually not perfect information games. Let us think a little more about chess. So if you think a little more about chess, what kind of a game chess is? Well, in chess you have a chessboard and the pieces are arranged in a pre-specified order. The rules of chess are known to both players, and so there is no hidden information. And then players alternately take a move, and it's also, the players also know how the game is won at the end. So it is a two-player perfect information game. Now, if we think about chess, suppose someone were to find a winning strategy for chess. This would mean that whoever played with this particular player, no matter who played with this particular player, this player will always win the game. What does that mean this player has done? So, what would it mean for somebody to find a winning strategy for chess? This means that no matter what game of chess, no matter whom they play with, no matter how intelligent of an adversary plays the game with them, they'll continue winning the chess games. What would it take for a person, or what would such a strategy look like? Well, that player must have figured out something, and that something is what we call a strategy in combinatorial games. What they would do is, they would know a move, and that would be their first move, such that no matter what the opponent does, they will have a move, such that no matter what the opponent does, they will have a move, such that no matter what the opponent does, they'll have a move, and so on, so that in the end, they will win the game. Of course, no such strategy, winning strategy, is known for chess. If somebody would have found out a winning strategy for chess, then chess would not be an interesting game at all. People will stop playing it, because if somebody were to know a winning strategy and memorize it, they would keep winning all the games, and that would make the game uninteresting. The reason board games like chess and Go are very interesting is because no one in the world knows a winning strategy for them. In fact, people don't know much about these games. They have to use their ingenuity to beat their opponent. And what is interesting in a chess game is the fact that it's a contest between two human beings who are using their intelligence to outwit each other. Many combinatorial games that are played between two players are known to be piece-space complete. So what we want to do now is look at a very interesting and natural combinatorial game that actually comes from a game that is played between people in a party or in a gathering. Let's look at this game. We will look at a game called Generalized Geography. But let's first recall what the game Geography is. There are two players in the game, or two teams in the game. Now, player one starts the game and says the name of a city, town, or a geographical location. After that, player two has to say the name of a city, town, or a geographical location. However, the rule is that player two must say a name which starts with a letter on which the previous name ended. So, the second player cannot just say any name, but must say a name from which the first player ended with. So, if the first player said Karachi, then the second player can say Islamabad, but cannot say Lahore. So that's the game. And then the turn goes back to the first player, and the first player does the same thing. And now once again the same rule applies to the first player. He must say a name which starts with a letter on which the previous name ended with. And the game now continues in this fashion. Now, what is important is repeats are not allowed. So if one city or town has been named, then it cannot be named again. People play this kind of a game in different cultures in a different way. So for example, in the West, this game is called Geography. However, here in the East, we like to play this game with poems. We play this game called Baatbazi, in which you say a poem, you say a line of a ghazal, and the next person has to say another couplet from a ghazal, and it must start with the letter that the last line ended with. Nowadays, teenagers play a game which they call Antakshari, which is played with popular songs. So Geography is the same game, but the restriction now is that you're supposed to say the names of cities or towns. So this is a two-player game, and the player or the team that loses is the one that cannot find a new couplet or a town or a city depending on the context. So that's the game. Now what we want to do is come up with a mathematical version of this game and investigate who will win this game. Now suppose we take the names of all geographical locations and make a graph. So each vertex of the graph has a label which is a name of a city or a town or a geographical location, and two vertices A and B are connected if and only if the last letter of A is the same as the first letter of B. So we can make this graph. So for example, here is a part of the graph. This is how it would look like. As you can see, in this graph, you're given nodes. They're labeled with names of various cities, and there is an edge from a city to another city if the last letter matches with the first letter. Now what we can do is we can think of the game Geography as being played on this graph. In terms of graph theory, how is this game played? In terms of the underlying vertices of the graph that I've just defined, how is this game played? Well, what does player one do? He says the name of a city or a town. So in other words, the player one chooses a vertex. Players continue now to select neighbors of the current vertex without repeating vertices until one of them fails to find a new vertex and loses. So if everyone knows all the names of all the cities in the world, then what we can do is we can write down a huge graph and place it on a board. Then the first team goes and picks a vertex, they say a name, and you can put a little marker on it. The second team now has to find a neighbor, pick a neighbor of it and put a marker there. And once a vertex is marked, you cannot remark it again. The game continues in this way. The current vertex, the team whose turn it is now trying to find a neighbor of it or mark one neighbor of it. These two teams alternate turns, and the first team to get stuck is the one that loses. So this game is called geography. Now, instead of playing this game on a graph, which is the set of all names of cities or geographical locations of the world, we can also play this game on an arbitrary directed graph, where now we take an arbitrary directed graph and player 1 picks a starting vertex, player 2 has to pick a neighbor of it, then player 1 has to pick a neighbor of that vertex, and player 2 has to pick a neighbor of that vertex, and the game continues like this. No one is allowed to repeat vertices, and the first person to get stuck is the one who loses, and the other team wins. So this game is what we call generalized geography. So now we define generalized geography. So once we have defined generalized geography, we can define the language which we call GG for generalized geography, which is the set of all directed graphs on which player 1 wins. See, if a directed graph is given and both players are infinitely intelligent, then who wins the game only depends on the graph, not on the intelligence power of the two players. So generalized geography is a perfect information game. There are no hidden moves. Initially, all the information that is there is made available to both the players. And so, for a given graph, either player 1 will have a winning strategy or player 2 will have a winning strategy. Let's see how a winning strategy of player 1 would be like. Player 1 has to choose a vertex such that for all choices of player 2, he can choose a vertex such that for all choices of player 2, he can choose a vertex, and so on, such that in the end, player 1 wins, which means player 2 gets stuck. So for player 1 to have a strategy, he must have a way of picking a vertex, so that no matter how the second vertex is picked by player 2, he can then again pick a vertex, so that no matter how the second player picks a vertex, he can then again pick a vertex and continue the game till in the end he gets player 2 in a situation where the second player is stuck. So if you think about it, this game has some similarity with quantified Boolean formulas. If you think of formula games, player 1 had to choose an assignment such that for all choices of player 2, player 1 had a choice, such that for all choices of player 2, player 1 had a choice, and so on, which made the formula true. So in this case also, there's some kind of an alternate quantification that is happening. And however, this quantification is not happening over Boolean variables. Now this quantification is happening over vertices in a given directed graph. So the question seems to be just like alternate quantified formulas. But is it? Now what we would like to do is, we would like to ask ourselves if a generalized geography game is as general as quantified Boolean formula game, as the formula game. Is it true that this game that we have defined and the computational question along with it, given a graph, who wins the game, how difficult it is for us to tell? Whether this problem is p-space complete, NP complete, what is the complexity of it? Can we come up with an algorithm which, given a graph, can tell us which one of the two players, player 1 or player 2, has a winning strategy? There are other very interesting questions that we can ask. Given a graph, is there an algorithm that, given a graph, will compute some kind of winning strategy for the first player, if it is a first player win game or not. A lot of these interesting questions are investigated in a subject called combinatorial game theory, and these games are perfect information games. However, what we want to do is just study this problem from a computational point of view. What we would like to do is show the following theorem. We would like to show that TQBF is polynomial time reducible to generalized geography, and therefore generalized geography is p-space hard. So actually what we would do is we'll reduce formula game to generalized geography, which means that if you give me a quantified Boolean formula, or if you give me an instance of the formula game, by looking at that instance, I can in polynomial time compute a graph such that if the original formula, quantified Boolean formula, were true, or if player 1 had a winning strategy for this formula game, then the new game, the generalized geography defined on this graph, would be a player 1 win game. This would mean that we can convert the question of formula games into questions about generalized geography, and therefore generalized geography is also p-space hard. Along with this thing, we would also show that generalized geography is in the class p-space. This would be a very simple recursive algorithm. In fact, what you can do is today go home and think about how you would devise a polynomial space algorithm that tells you whether player 1 wins a given generalized geography game or player 2 wins it. Well, all here I am asking you is to devise a polynomial space algorithm, not a polynomial time algorithm. And if you think about it, you'll be able to come up with a simple recursive algorithm which would only require polynomial space. Once we do that, these two things would show us that generalized geography is also p-space complete. We will prove this theorem next time, but let us now discuss some very interesting results from combinatorial games. Well, our main interest is complexity theory, and what happens is many of these combinatorial games turn out to be p-space complete if you appropriately define these games and formalize them. It is known that appropriately defined versions of many games that people like to play are p-space complete. These include chess, for example. If you take an n by n chess, so this is not a chess game which is played on an 8 by 8 board, because that game would become a finite game and therefore in principle can be solved in a finite amount of time. Of course, that finite amount of time is so large that nobody has solved this game so far, but an n by n chess game, and given an arbitrary placement of the chess pieces on an n by n chess game, telling whether player 1 wins or the first player, or whether white wins or black wins, turns out to be p-space complete. There are other games. Another game is called Go. Go is a very interesting board game, and it's even simpler than chess. However, the rules are simpler than chess, but people who play it say that it is a much deeper and more difficult game than chess is. And of course, n by n chess, given an arbitrary positioning of the pieces, telling who wins this game is also p-space complete. Here I would encourage you to go onto the internet, get onto Google, and look up both these games, chess and Go, and search for chess and p-space completeness, and Go and p-space completeness, and another game called Hex, which also turns out to be that its appropriately defined versions are p-space complete. Search for them and look at these interesting results. It's fascinating that games which were invented naturally for people, by people to simply entertain themselves or challenge themselves, or intellectually satisfy themselves turn out to have this deep connection with complexity theory? Well, in the next lecture, we would look at the formal proof that generalized geography is p-space complete. I hope you've enjoyed today's lecture. I'll see you next time. Thank you and goodbye.